Welcome to this online class of mathematics. Today we are going to discuss complex analysis. In this one, we discuss winding number, index of a curves about a point. Basically, in this particular lecture, our aim is to discuss Cauchy integral formula or Cauchy theorem. But before proceeding further, we define few things. First one is a winding number. What is a winding number of a particular curve? It says that if gamma be a closed rectifiable curve in C, rectifiable means we have already mentioned what is the meaning of the rectifiable. Rectifiable means it is of finite length. It is of finite length, or it is of bounded variation. It is of bounded variation. So, if gamma is a closed rectifiable curve, then for each a in C minus trace of gamma. Here, trace of gamma is nothing but this consists of gamma of t such that t belonging to the domain, जो भी domain हो, t belonging to a domain. All right. Okay. So, its winding number is defined by, and it is given by this particular winding number of gamma about a, which is equal to 1 upon 2 pi I integral over gamma 1 over z minus a dz. And this particular number is called index of a gamma with respect to point A, or winding number of gamma around A. So, either you call winding number of gamma around A or index of gamma with respect to A. It means winding number is nothing but it is a number of times. Suppose this is a particular point A, the number of times the particular curves wraps this particular. Suppose if gamma is the orientation of gamma is in this direction, then the number of times this gamma wraps this particular point is known as a winding number. So, this particular thing has significant features, and here are few facts which are related to the winding number. First one is the winding number of gamma about A is always an integer. This is an important and crucial point, that the winding number of a particular curve is always an integer. And if you want to define the winding number of a negative of a particular curve, this is nothing but this is a winding number of gamma, negative of the winding number of gamma. And if you want to find out the winding number of a sum of two particular curve about A, this is nothing but this winding number of gamma with respect to A and winding number of gamma with respect to sigma. There should be sigma. So, here is a little mistake. So, I am erasing this one, and this particular thing is a sigma. So, winding number of sigma with respect to A. Another important thing is, this is a gamma is a closed rectifiable curve in C. Gamma, if gamma is a closed rectifiable curve in C, then important thing is this winding number with respect to A, index of gamma with respect to A is constant for all A belongs to component of this. It means C minus singleton gamma may have several components. If our A belongs to component, then winding number of gamma with respect to that point is always constant for all A in that component. It means if you change the point in that component, then there will be no change in the winding number. And another crucial fact is here, the winding number of gamma about A is 0 if A belongs to the unbounded component. So if A belongs to unbounded component, then its winding number is always 0. Another crucial facts related to the winding number is this one. If you define a mapping f from C minus this trace we have already defined to C, if we define f of A is equal to winding number of gamma around A, then this particular function is a continuous function. So these whatever we have discussed so far, that is not a part of the syllabus, but these are important thing in the Cauchy theorem and Cauchy integral formula. So that's why these facts are really important. Okay. These facts are really important. Okay. So now I'm moving towards the Cauchy theorem and Cauchy integral formula. Okay. Cauchy theorem and Cauchy integral formula. So let me erase this one and then continue. We have already defined, we have already proved a theorem. We have already proved a theorem. We have already proved a theorem which simply says that which states that if D is an open unit disk or open disk, if D is an open disk and F is analytic function, on D, and gamma is closed rectifiable curve, closed rectifiable curve in D, then the integral of f about this gamma is equal to 0. This we have already discussed in the previous classes. Here my question is, can be generalized. Okay. Okay. So here our question is, can we generalize this particular result for arbitrary domain or arbitrary region, or what are the reason for which this kind of results are true? Okay. So here our first question is, what are the reasons, what are the reasons in which in which this kind of result is true. This kind of result is true. Result is true. Result is true. So to see this one, we are I'm going to take a particular example. I'm going to take a particular example which give you some idea about the reason for which the above result is true. So this particular example, if you take in this example, if you take our reason, suppose z is equal to c minus singleton 0 and f of z is equal to 1 over z for all z in Z, then clearly this function is continuous, this function is analytic, then clearly this function is analytic in D, in Z, and take gamma of t is equal to e to the power it, where e to the power it, where 0 is less or equal to t is less or equal to 2 pi. Again, it is obvious that it is clear that gamma is a closed rectifiable curve. Closed rectifiable curve. Now consider this integral. Now consider the integral. Now consider the integral of gamma, integral of f about gamma. This is given by integration 0 to 2 pi f of gamma t into gamma dash t dt, and this is exactly equal to integral from 0 to 2 pi 1 over e to the power it into iota e to the power it dt, and this is exactly equal to I 0 to 2 pi, and this e to the power it and e to the power it gets cancelled and you got 1 here, so this is equal to 2 pi I. So now one can observe that in this particular region 1 over z is analytic, gamma is closed rectifiable curve, but integral is non-zero. It is obvious that this is not equal to 0. It means for this particular reason, Z, our Cauchy theorem fails, which we have already proved for disks. It means, what is the problem here? If you observe this particular reason, then let me show it. In case of the disk, if it is a disk, so in the case of disk, there is no whole kind of a things. It means everything is in the domain. But in our case, if I take this is a C, then in our case we have deleted this particular thing, means we have deleted this particular origin. It means this G, which is equal to C minus 0, contains a hole, but disk does not contain hole. This is the significant difference between these two. So in general, we prove one can we prove a particular result, that this particular Cauchy theorem is true for those regions which are simply connected. It means if f is analytic, in a simply connected domain, simply connected domain means a connected domain which doesn't contain any holes. So if f is analytic in a simply connected domain, then the integral of f about any closed rectifiable curve is 0. Integral is 0 for any closed rectifiable curve in closed simply connected domain Z. For any closed rectifiable curve, closed rectifiable curve in Z. Okay. So now I'm moving towards the Cauchy integral formula, but before that I'm going to provide a lemma, which is more useful in finding out different versions of Cauchy integral formula. What does it says? It simply says that let gamma be a closed rectifiable curve, let gamma be a closed rectifiable curve in C, and phi is a function defined and continuous continuous on trace of gamma, defined and continuous on trace of gamma. For each m greater or equal to 0, for each m greater or equal to 0, let capital Fmz is equal to integral over gamma phi of w upon w minus z whole to the power m dz. For each m greater or equal to 1, let Fm is equal to this for z belonging to C minus singleton gamma, and suppose that this is equal to Z. Alright. So this is our assumption. Then each Fm is analytic, then each Fmz is analytic in Z, and Fm dash z is equal to m times Fm plus 1 z. Okay. So this is our statement. So now I'm going to prove this one. So this is an interesting thing, and we are going to prove this. So here we have only assumed that this function phi is defined and continuous on the trace, so that you can define this kind of an integral. And our aim is to show that Fm is analytic. So before proving Fm is analytic, we initially prove that Fm is continuous. So our claim is initially we proved that each Fmz is continuous. Initially we proved that each Fmz is continuous. Okay, so each Fmz is continuous. For this one, let z0 belonging to Z, I have already mentioned what is Z. Let z0 belonging to G, V an arbitrary element of Z. Let z not belonging to Z. So if I have already mentioned it is an element of Z, so we should only write let z not belonging to Z be an arbitrary element. Okay. So suppose this is an arbitrary element. So we want to prove that our claim is our claim is that Fmz is continuous at z naught. Fmz is continuous at z naught. For this one, for this consider the expression, consider the expression this mod of Fmz minus Fmz naught. All right. So by definition of Fm, you have mod of integral over gamma. So integral over gamma we have here as well as here, so it can be taken as a common. Phi of w is in the both one. Phi of w is here, phi of w is here. So the next thing is a 1 upon w minus z to the power m minus 1 upon w minus z naught to the power m and dw and then modulus. Okay. So here we use this particular factorization of this particular thing, and this become equal, this is equal to mod of integral over gamma phi of w then the square bracket 1 upon w minus z 1 upon w minus z minus 1 upon w minus z naught. So you got this one, along with a summation k varies from 1 to m 1 upon w minus z to the power m minus k and w minus z naught to the power k minus 1, and this thing is closed, dw and then the modulus. I think here we use I'm giving the reasoning, and that reasoning is a to the power m minus b to the power m. This is nothing but a minus b in one bracket, and in another bracket you have this summation k varies from 1 to m a to the power m minus k, and another is b to the power k minus 1, and this is all right. So we have this particular result. So we have used this particular result. Okay. So now I'm moving further, and then this particular thing can be written as this is equal to mod of integral over gamma phi of w, and if you solve this particular section, then in this particular section you will get z minus z naught upon w minus z and W minus Z naught, and the next thing is a summation. K varies from 1 to M, 1 upon W minus Z to the power M minus K and W minus Z naught power K minus 1, and this symbol close dW modulus. Okay. So suppose that this particular equation, this particular relation is star. Now I'm going to estimate this one. To estimate this one, because since we have already chosen, since Z naught belongs to C minus this trace of gamma, which is equal to Z, and the trace of gamma, this is a trace of gamma is compact set. It is a compact set. So it is a compact set. So therefore, since this is equal to this and trace of gamma is compact set, therefore the distance of Z naught from this trace will be positive, strictly means it will be positive, and so choose that this is equal to R. Suppose that this is equal to R, because we want to show the continuity at the point Z naught. So here whatever Z we have chosen, that is close to Z naught. Whatever point we have chosen, that is close to Z naught. It means here, therefore this is equal to this. Also assume that और भी हमने क्या माना कि the mod of Z minus Z naught, it means distance between Z and Z minus Z naught. Here distance is nothing but modulus function. This particular thing is defined as a minimum of Z naught minus W, such that W belongs to the trace of gamma. So this is the definition of this particular thing. So here I am assuming our Z is close to Z naught. It means it is less than epsilon, because we want this one, and suppose that this is less than or equal to 1 upon 2R, means it is inside, Z is inside the disk of radius half R by 2. Now if we consider this particular picture, then clarity emerges. Suppose this is your gamma. Okay, this is your gamma, and suppose this particular point is a Z naught. If this particular point is Z naught, then the closest point of curve, closest point of gamma from Z naught, suppose this is the closest point of this one, so this particular thing will be R. So here I have taken a disk of radius r by 2. Suppose this is r, so let me erase this one. Okay, so this total length is r, but I have taken this particular radius 1 by 2r, means r by 2. So z lies somewhere inside this disk. So z lies somewhere inside disk, anywhere, either here or anywhere, but inside this disk. Okay, so if we if assume this, okay, now observe that now observe that what we are observing here. Now we are observing that if you want to search what is the distance of w minus z naught, so of course w is varying on the path, w could be anywhere, so its distance will be always greater or equal to r, because if w is here, if w is on this point, then it will be r, otherwise it will be greater than r. So it will be greater than r, and if it is greater than r, then it will be greater than r by 2 also. Similarly, mod of w minus z will be greater or equal to r by 2. How? Because if w is at this point, अगर मान लीजिए कि w यहाँ पर है, then and z is here, then its distance is r by 2, and in other cases, if z is here or anywhere else, then in another cases it will be greater than r by 2. So it means in each cases w and z, the difference between w and z will be greater than r by 2, because w is varying throughout. The closest point will be, if w is at this point, अगर w यहाँ पर है, then it will be closest point, and because this distance and the distance of this point is r by 2, this particular distance is r by 2. So if z is here, then its distance is r by 2, otherwise if z is at this point, then it will be greater than r by 2. Here it will be greater than r by 2. In other cases it will be greater than r by 2. So using these estimates, now we observe these two. Okay, using these estimates, star can be written as, जो हमने स्टार रिलेशन लिया था वो लिखा जाएगा. Using these statements, using these facts, along with the continuity of function phi on the compact set and the compact set this, using these facts along with the continuity of the functions and the compact set this, star can be reduces to, star can be written as, mod of fmz minus f m z naught, this is this is less or equal to, this is less or equal to, if you take the modulus inside, then this become less or equal to integral over gamma mod of phi w mod of z minus z naught, mod of z minus z naught, and if you multiply this one here, then you can have this summation k varies from 1 to m 1 over w minus z naught to the power w naught minus z, first I am going to write. So w naught minus z to the power m minus k plus 1 into w minus z naught to the power k, this modulus, here is a modulus also, so this mod and then mod of dw. Is it all right? And because phi is a continuous on the compact set, so this is bounded, so this is less or equal to, not lesser, strictly less than, basically this becomes strictly less than capital M, where it is a bound for this, and this is delta for the bound for this, which we have already written. And what about this? What about this? We get summation k varies from 1 to m, k varies from 1 to n, and this particular 1 upon w minus z is less than 2 upon r, 2 upon r, just have a, take this, use this particular thing, 1 upon w minus z is greater than 2 upon r, so you get here 2 upon r whole to the power m minus k plus 1, and this also less than 2 upon r, so this is 2 by r whole to the power k, and this integral becomes the gamma mod of d, so you get this one. Okay, so and here I should mention the mod of phi of w, this is less or equal to m because it is bounded. So this particular thing become okay, this is exactly equal to delta small m 2 upon r whole to the power m plus 1, the total variation of gamma, because we want to show that this is our aim, this is our aim, this is our aim to show that key this is less than epsilon, this is less than epsilon, choose our epsilon which is equal to minimum of r by 2, we have already taken this one, and what is about this one, if you take, so epsilon into r upon 2 to the power m plus 1 upon small m capital M total variation of gamma. So if you choose our delta, so that then clearly then clearly mod of fmz minus fmz naught, this become less than 0 for all mod z minus z naught is less than delta. So this implies that f m z is continuous at z naught. Since z naught was arbitrary, since z naught was an arbitrary number, z naught was an arbitrary element of z, which is equal to c minus singleton gamma. Therefore fmz is continuous on z. fmz continuous है z पर. Okay. Next thing is to prove the analyticity of m second है. m second is to prove that fmz is analytic, it is not only continuous but analytic in z में analytic. So to prove this, observe this particular thing, relation. Observe this particular relation star. Okay. So to prove this, again observe this particular relation star. Star relation को I am writing once again. So to prove this, observe the relation. Again consider the relation star. Again consider the relation star for z naught belonging to z. So we have mod of, in this case I'm not going to write mod. So take fmz minus fmz naught. We have obtained here, this is integral over gamma phi of, this is integral over gamma. Okay, integral over gamma phi of w z minus z naught summation k varies from 1 to m 1 over w minus z to the power m minus k plus 1 and w minus z naught to the power k dw. This was our expression. So using this we can write, this implies that fmz minus m z naught upon z minus z naught, and I am taking, because we want to take the limit z tending to z naught. So this is equal to limit z tending to z naught, and because z minus z naught is independent of w, so that's why this thing is taken here. So now we have integral over gamma phi of w and summation, because it is a finite summation, so summation can be taken out also because it is a finite summation. So if it is not it is not a finite summation, then things become complicated, but here we have a finite summation, so that's why there is no problem. And also we can take upon w minus z naught to the power k, then whole upon w minus z whole to the power m minus k plus 1 dw. Okay, so let me insert one more page after this one. So we got this one. All right, so before proceeding further, observe the few things. First is a integral and summation. We have interchanged these two because we have a finite summation, so that's why these two can be interchanged. Similarly, limit and this can be interchanged. Limit और इसको भी interchange कर सकते हैं. There is a reason behind this one. Limit and this can be interchanged. So it means this can be written as summation k varies from 1 to m, limit z tending to z naught, integral over gamma phi of w upon w minus z naught to the power k, and then whole upon w minus z to the power m minus k plus 1 dw. Okay, so few things can be observed here. So one, because since, so suppose it is double star, suppose this is a double star, since w belongs to this trace and z naught belongs to c minus this trace, so this implies that w is different from z naught. So since this belongs to this and this implies that this is equal to, therefore phi of w upon w minus z naught to the power k is continuous on trace of gamma. This become continuous on trace of gamma. All right, this become continuous on the trace of gamma. And we in the part first of the proof, in the part first of the proof of the in the part first of the proof, we have shown that okay, in the part first of the proof we have shown that we have shown that integral of phi w upon w minus z to the power m dw is continuous at z belongs to c minus trace of gamma. This is continuous at this for each continuous function phi defined on this trace of gamma. So in our case, therefore the integral appeared in, therefore the integral appeared in double star is also continuous. इसलिए इंटीग्रल जो डबल स्टार में पे वो भी कंटिन्यूस होगा. And we also know a fact, we also know a fact about continuous function. We also know a fact about continuous function that the limit of z tending to z naught f of z is equal to f of limit z tending to z naught z, and this is equal to f of z naught. So therefore keeping this fact in mind, keeping this fact in mind, double star can be written as डबल स्टार कैसे लिखा जाएगा. डबल स्टार क्या था, that was limit z tending to z naught f mz minus f mz naught upon z minus z naught, that was equal to summation k varies from 1 to m limit of gamma. This is a limit of z tending to z naught. We have taken limit inside phi of w upon w minus z naught to the power k upon w minus z to the power m minus k plus 1 dw, and this is exactly equal to summation k varies from 1 to m integral over gamma phi of w upon w minus z naught to the power k upon w minus z naught to the power m minus k plus 1 dw, which is equal to summation k varies from 1 to m integral over gamma phi f w upon w minus z naught to the power m plus 1 dw, and this is exactly equal to m times of integral over gamma phi f w upon w minus z naught to the power m plus 1 dw, and this is exactly equal to m into f m plus 1 at z naught, and this particular thing is f m dash at z naught. This implies that fm is analytic at z naught, and hence it is analytic in Z. This proves the result. Okay, so now we are finishing this one. We will discuss the next thing in the next class.